her goal is not in her.
Hi everyone, today in this video we will discuss together a very interesting topic, and it's a bit complicated, which is called radiation heat transfer. Radiation heat transfer, when we deal with it, is not the same way as we dealt with conduction or convection heat transfer, because radiation heat transfer has another parameters to control the process itself, and it has different rules, or it has different ways to analyze what is the radiation heat transfer and how different bodies act together to receive the net radiance. Okay, first of all, to be more simple and to understand this topic with a nice easy way, I want to explain to you what is the parameters which is affecting the process. In general, radiation heat transfer is affected by or is controlled by two main parameters, which is the temperature of the body and the wavelengths of the radiant itself. What does it mean? For example, if I have a body here, okay, and I have a source of radiant or a source of radiation energy, and this source of radiation energy, for example, a sun, to make it simple or to make it more understandable, the sun has another or different radiation energy at different wavelengths. Okay, each body in this area or on this planet, the Earth, can receive an amount of this radiation energy depends on the wavelengths. For instance, my body as a human being doesn't receive all of the radiation coming from the sun, because my body receives just a certain wavelength or just a certain range of wavelengths. Beyond this range, my body will reflect it back to the surrounding. Okay, for example, if I have a black car, the surface of this black car will receive more radiation energy from the sun comparing to a white car. Okay, so the wavelengths of the black body, it will have a higher range or a wider range comparing to a white or another kind of colors. Okay, so the first parameter, which is controlling the radiation heat transfer process, which is the wavelength. The second parameter is the temperature. For example, if I have the sun, which has 5,800 Kelvin, the surface area of the sun, it has a radiation, or it can emit more radiance comparing to another surfaces which has less temperature. Okay, please remember, when the temperature is high, the wavelength is less comparing to if the temperature is low. For example, if I have a surface area with a high temperature, so almost or the amount of the energy which is emitted from this surface, it will have shorter wavelengths comparing to a cooler surface. Okay, great. In general, this emissivity or this emissivity energy is coming from any surface, is including an electromagnetics, or it is an electromagnetic energy. Okay, so all materials absorb this electromagnetic, but it is depending on wavelengths, as we mentioned before. My body doesn't receive all of the radiance coming from the sun, it receives a certain wavelength range. Okay, so this is the first thing you have to be aware of, what is the wavelengths and what is the temperature, and how they can affecting the radiation heat transfer process. Okay, in general, we can classify the bodies into three main categories to make it simple and easy to understand the radiation heat transfer. There is something called a black body, which is a theoretical body, and I will explain this later. And there is something called a gray body, and there is another types of bodies called a real body, which is the real one in our actual or real applications. Okay, the black body is a theoretical body. What does it mean? It emits the maximum theoretical energy, which is the radiation energy, at all wavelengths. For example, if I assuming that the sun is a black body, so the sun will emit like all of the theoretical energy at all wavelengths. So you will find the energy coming out, or the energy created, or the energy delivered by the sun having all of the wavelengths. Okay, the black body itself absorbs all of the radiant energy falling into it, regardless what is the wavelength. Okay, real body emit less than the black body and absorb less than the black body. So the black body is a theoretical body to deal with. Like, for example, if I assuming there is a black body and this black body facing the sun, okay, so all of the radiance coming out from the sun traveling towards this black body, it will be absorbed regardless what is the wavelength. There is nothing will be reflected back to the surroundings. Okay, so a black body is a theoretical body. It doesn't exist in reality, but this is the theoretical one. It emits and it is absorbed all of the wavelength energy. Okay, here there is a diagram explaining how is the black body emissivity, or how is the energy emitting by a black body varies with the wavelength itself and the temperature. For example, here I have the wavelength with the emissive power, or which is the intensity. When the temperature is increasing, the emissivity or the emissive power is increasing. For example, if I have the black body at a room temperature here, so the area under the curve representing the emissive power, so here is the emissive power from this black body is less than when the black body temperature will be 800 Kelvin, is less than when the black body it will be at the sun surface temperature, which is 5800 Kelvin. Okay, so the emissivity or the emissive power is changing or varying by the varying the temperature, or with the temperature variation, and the wavelength, it doesn't have that effect on the emissive power if we assuming a black body. There is three types of wavelengths, or three ranges of wavelengths. There is a microwave, and there is infrared, and there is ultraviolet. Okay, ultraviolet, which is very small wavelengths, and infrared, which is in between the micro and ultraviolet. Okay, like for example here you will find the wavelength or the emissivity power, it will be very small comparing to the sun one, because the sun emits different or higher range of the wavelengths as we see here. Okay, remember that the emissive power we refer to it as an E. Okay, so E means the emissive power. Intensity, which is I. What is the relation between the intensity and the emissive power? Intensity is equal to E, which is the emissive power, divided by the surface area. If we go back to the conduction or convection, intensity is the same as the heat flux. Okay, so is the total power divided by the surface area. Great. So the first body is a black body, which is absorbed and emits all the range of wavelengths. Okay, the first law which we have to concern during studying radiation heat transfer is called Stephen Poltzmann Law, and it says, or Stephen Poltzmann assuming, or he found out that the total emissive power from a black body, referring to B, okay, is equal to the surface area of this body times sigma, which is Stephen Poltzmann constant, times the temperature of this body with a power 4. Okay, please remember that the temperature, when you are calculating a radiation heat transfer equations, put the temperature in a Kelvin, not in a Celsius. Okay, so this is the total emissivity, or this is a total emissive power from a black body. Is a function of the temperature. There is no wavelengths including, or there is no wavelengths involved in this equation, because the wavelengths doesn't affect the emissive power by a black body. Okay, Stephen Poltzmann constant, it has a constant value which is 5.67 times 10 with the power minus 8 watt per meter square Kelvin with the power 4. And the temperature, as we mentioned, that it will be an absolute temperature, which is a Kelvin, and the surface area with meter square. Okay, so this is the emissive power from a black body. Let's have a small example or simple example to explain how we can deal with a black body. Calculate the total emissive power of a sun by treating it as a black body. It has a diameter of 1.8 times 10 with the power 9 meter and surface temperature 5800 Kelvin. Okay, how we can calculate E? Just back to this equation, we can calculate the intensity, and we can calculate the surface area of the sun. Multiplying both terms together, you will have the total emissive power. So this is the intensity, which is I, as we mentioned before, is equal to sigma, which is Stephen Poltzmann constant, times T with the power 4, which is the absolute temperature of the sun. So I have the intensity, and then I calculated the surface area of the sun, because the sun is a spherical one, so it's pi d square when d is the diameter of the sun. So I have the total surface area. Multiplying these two terms together, I will have the emissive power, which is equal to 6.6 times 10 with the power 26 watt, which is too high. Okay, so assuming that the sun is a black body, it will emit this total power. Okay, this is the first law, which is called Stephen Poltzmann Law. Please just remember it during your calculations. The second law is called inverse square law, and be careful when you deal with this law, because it's a bit tricky, but it is very important. Okay, so if I have a black body here, which is the sun, and I have another body here, okay, I know now how to calculate the intensity of this black body at this point, okay, which is the total emissive power divided by the area of this surface, correct? What if I want to calculate the intensity of this power or this body, which is away from the first black body with a distance, let's say we call it x, okay? Of course, the intensity of, or the power or the strength of the emissivity at this point, it will be much stronger than this point. This is what the inverse square law explains. If I have the black body at this point and I want to calculate the intensity at this point, and this distance it will be x, let's say, for instance, okay, so the area increase as a square distance, like when x square increase, the area will increase. Let's say here this area is much higher than this area, correct? So the intensity it will be reduced. So the intensity reduce with the inverse of the square of the distance. Let's imagine what is the intensity. For example, if you have a laser beam, okay, and this laser beam is very concentrating in very small area, like for example, if I put this beam in a very tiny small area, the intensity or the power of this laser beam it will be much stronger than if I spread this beam over a larger area. Okay, this is what the intensity I representing. What is the power of the emissive energy comparing or as a relation of the surface area. So how to calculate the intensity, the intensity at different bodies away from the first body or the black body with a distance x. This is the main equation. The intensity is equal to sigma, which is a Stephen Poltzmann constant, times T with the power 4, which is a temperature or the absolute temperature with the power 4, times the black body or the first body radius square divided by the distance square. Okay, so here for example, if I calculating like this is a small example, like if I want to calculate the intensity at a distance of 1.5 times 10 with the power 11 meter from the sun, calculate the intensity of the solar radiation at the edge of the earth of atmospheric. For example, if I have the sun here and if I have the earth here, and the distance between the sun and the earth is equal 1.5 times 10 with the power 11 meter. So I have here the solar distance, which is 1.510 with the power 11, and I have the sun radius, which is the black body radius, and I have the intensity, which is the total emissivity calculated before in here, divided by the surface area of the sun. So I have the intensity which is coming or which is reaching the earth or which is the earth receiving from the sun. So if the sun emits this total power, okay, we receive only this amount of power, okay, but remember this is per unit area. So if I have this number, which is I times the surface area of the earth, I will have the total power in watt. Great. So I have two main laws now. The first one is the Stephen Poltzmann law, which is calculating the total emissive power from a black body. The second one is the inverse square law, which is calculating the intensity received by another body away from this black body with a distance x. Okay, there is another way to call or to calculate this intensity received by the earth in this example, but this is I prefer to use this way or this equation, but I will explain the other way just in case. Okay, so if I have a sun here and this is a black body and I know what is the total intensity or total emissive power, and I have the earth here, okay, and I have the distance between this point to this point, which is equal to x, correct, to this point, from this point to this point, and I want to calculate I received by the Earth from the Sun. The first way to calculate it is using this equation. The second way is to have an imaginary body like this, which has a radius or a diameter of x, okay? And I know that this body emits this total power, which is E, so I can have this E divided by the surface area of this imaginary body with respect of this x as a diameter. I will have the intensity which has been received by the Earth. This is not very accurate, but I'm just giving you an idea how people using it. So the surface area of a sphere with a radius of 1.5, 10 with the power 11. If we go back to the main example, you will find this is the distance. So I assumed that this imaginary body has a surface area of 1.5 times 10 with the power 11 meter. So I calculate the total surface area as we mentioned, and I know the total emissive power from the Sun calculated before. So I just divide the total emissive divided by this imaginary area. I will have the same number, because this is very simple example. But if you go through a more complicated calculations, you have to use this equation because this is more accurate. Okay, now we understood what is the black body. We said that the black body will emit the whole of the wavelength range, or all wavelength range, and it will absorb all of the intensities. Just send it to it, and there is no wavelengths involved in the calculation of the black body radiation. Okay, what about real body? What is the difference between the real and the black body? Real body, if I have the Sun here, I'm just imagine like if I have the Sun here, and this Sun sending an intensity or incident is equal to I, which is watt per meter square, as a per meter square relating to the Sun, remember? And I have another body. This body will receive some of this incident or intensity, and it will reflect some of them, and it will transmit some of them. So there is some reflective, some transmitted, and some absorbed. How we can calculate this as a function of I? So I have three samples or three parameters, which is called absorptive, which is alpha, and I have the reflective percentage, which is rho, and I have the transmitted percentage, which is tau. The total is 3, or the sum of these three percentage, it will equal to 1, which is mean each of those it will be less than 1. Okay, for a black body, as we mentioned, it will absorb all of the arrays which has been sent to. So the absorptive or the alpha, it will be equal to 1, which is mean there is no transmitted and there is no reflected. Okay, because if this one alpha and tau, it will be equal to 0. For opaque body, which is opaque material, which is not black, okay, the transmitted value, it will be 0. So there is some will be absorbed and some will be reflected only. Okay, some will be absorbed and some will be reflected, because the transmitted one, it will be equal to 0. For example, if I have a glass and I have some sun arrays, there is some transmitted through this glass. But if I have like tinted glass, let's say, and I have some sun arrays or some beams, you will not find any transmissions. Okay, so tau is equal to 0 for opaque materials, and alpha it will be equal to 1 for a black surface. So this is for real body. For real body you have to consider how much it will be absorbed, how much it will be reflected back, and how much it will be transmitted. For a black body it will absorb the whole wavelength range, so alpha is equal to 1. For opaque body tau is equal to 0 because there is no transmission. Okay, what is the emissivity? So this body receives some incidence or some intensity or some emissive power. It absorbs some and it reflects some and it transmits some. The question is, this absorbed energy, where it will go? Like if you go to a microscopic scale, you will find this energy which has been absorbed. It will make the material molecules more active or more excited, and it will be like high vibrations inside this material or this body. Due to this, the temperature of this body will be increasing because the vibration or the molecular vibration will be increased. So this body want to get out or to get rid of this energy stored inside it. How it will be rejected or how it will be transferred from this body to another body? There is two ways. The first way, it will be radiation, which is 100% guaranteed, and the another way it will be by conduction on convection. In case if this body in contact with a solid surface, it will be by conduction, and if this body, for example, is just touching some liquid or there is an air coming over it, so it will be by convection. Why I'm explaining this now? To tell you, like, all of the three heat transfer mechanisms working together. In real applications, when you deal with a heat transfer, you have to consider radiation and conduction and convection all together. Back to the radiation now. So the absorbed energy by this body, it need to be rejected. So the temperature of this body will get back to normal. So how this body will reject this amount of absorbed energy? It will be by radiation. Radiation means the emissivity. What is the emissivity of this body? Like how much power can emit from this body and how much power can be still stored inside it by absorbed one. So if I want to calculate an emissivity at a wavelength which is lambda, okay, it will be as a ratio of the emissive power at a wavelength lambda divided by the emissive power of the black body at this wavelength. So if I calculate this ratio, so I got the emissivity, which is epsilon. Okay, so epsilon is how much power can be emitted from this body. Remember that I told you before that there is two or three main categories of body, which is the black body discussed earlier, and I have the gray and red body. What is the difference between a gray and red body? A gray body has an emissivity which is less than unity. Okay, in any way, like in red or gray body, the emissivity epsilon must be less than unity, must be less than 1. So the gray body has an emissivity less than unity, but it is the same at all wavelengths and temperature. What does it mean? Like, for example, if I have a gray body here, and this gray body has a temperature T1, and this emits a amount of energy, let's say, for example, lambda 1, which is the first wavelength and temperature. If I go to another or the same gray body and I change this wavelength to lambda 2 and the temperature of this gray body become T2, you will find the emissivity of the gray body at these conditions. It will be the same, the gray body or the emissivity of the gray body at different conditions is a constant. Okay, in a real body the emissivity is less than 1 and it varies with the wavelength and temperature. Remember, at the beginning of this lecture I told you there is two main parameters affecting the emissive power or the radiation heat transfer, which is the temperature and the wavelength. So in real body the emissivity or the emissivity quantity, it will be controlled by the temperature and the wavelength. For example, if I have a real body and I calculating the emissivity at let's say for example T1 and lambda 1, if I go to another temperature and wavelength, I will have another value of the emissivity. It's not the same like the gray body. Okay, so here there is very simple diagram explaining the black body and real body. Let's see, for instance, here the emissivity power is varies with the wavelength. As you see, there is a fluctuation here, but the black body, it will be smooth because the emissivity of the black body it will be equal to 1. Emissivity is like, for example, if here the black body, so epsilon p, and here it will be the emissive power of the black body is the same, so this equal to this, it will be 1. Okay, so this is the difference between the black and real body emissivity or the emissive power. Black body is a theoretical one and it emits the maximum power at all wavelengths. Like at all wavelengths it will be the maximum power. At this point it will be higher than this, at this point it will be higher than this. Okay, and as we said before, the intensity of the black body or the black body, it will be sigma times the power 4 times the surface area, but the real body, it will be the emissivity times the intensity or the or I, like, which is emissive divided by the surface area. Okay, okay, great. So if I go back here, like or if I go to this diagram, this is explaining what is the relation between the black body and the gray body. Okay, as we mentioned before, there's the black body at all wavelengths like emits the maximum power, as we said. Okay, but the real body or the gray body, it will be less than. So if I want to calculate the total emissive power of the gray body, it will be with respect of the emissivity of the gray body, and for a black body it will be sigma T with a power 4. This is per surface area, of course. Okay, okay, black body emissivity is equal to 1, gray body is less than 1 as real body as well. Okay, so now we discuss the first law, Stephen Poltzmann. The second one, the inverse square law. The third law is Kirchhoff law. What is Kirchhoff law indicates? Kirchhoff law is saying at any wavelength lambda for any body, epsilon is equal to the absorption, like absorbing value or absorbing energy, which is alpha. So like if I say, for example, like if I have a body and this body absorb this amount of the energy, this amount, it will be similar to the amount emitted by this body as the same wavelength. Okay, so real body absorptivity varies with the wavelengths and it should be less than 1, and the absorptivity is alpha, as we mentioned before. And for black body absorptivity, all the wavelengths, which is equal to 1. We mentioned this earlier. Okay, Gray body's absorptivity is the same at all wavelengths but less than 1. So in rail and the gray body is less than 1, but this varies with the wavelengths. This is the same at all wavelengths, and the black body is equal to 1. This small like a schematic diagram, it will show you how the radiation heat transfer process in real life happen. So if I have a sun here, the sun, it emits some of let's say for example energy like electromagnetic energy, and this energy has been received by a body which is a real body. This body will absorb some of this energy and will emit some of this energy as well, and there is some reflective. Why I didn't assume that there is a transmitted one? Because I assume that this body is opaque, like a real one, like is not a glass, is not transparent. Okay. Be careful when you read this sentence. Solar radiation energy concentrated in a short wavelength due to high surface temperature. So as I mentioned before, that when the temperature is high, the concentration will be in a shorter wavelength. Here this body temperature, it will be of course less than the sun surface temperature, so it will have long wave due to low surface temperature. Okay, so in real applications, like if I have solar power panel, for example, what is our objective when we install or when we fabricating this panel? We wish to have a high absorptivity to absorb the most of the wavelengths and less emissivity, because I don't want this panel to emit any power to the surroundings, because as much as I receive or as much as I absorb and stored inside these cells, which is silicon cells, I can convert it to an electricity. Okay, so the emissivity should be less as much as we can. Okay, what is the greenhouse effect? The greenhouse effect, when I have a surface and this surface emits a high amount of energy or electromagnetic energy, the surrounding temperature, it will be higher. Okay, this is the greenhouse effect, which is affecting the temperature of the surrounding, which is melting all of mountains, icebergs, all of these things. So greenhouse effect is a function of the emissivity of the bodies inside the universe. For example, if I have trees, the tree surface area, for example, has emissivity less than cars, so the trees will absorb like power much higher than cars or than building walls or whatever. In real application, radiation heat transfer is very important mechanism to consider, and it has a very high effect or very sensitive effect on the surroundings. Okay, so this diagram, it will explain for you how the bodies dealing together with the radiation interference, and how each body receive from the neighboring body the amount of the heat transfer, and what is the emission or what is the total net emissive power can be between these two bodies. Okay, if I assume that there is an enclosure, and this enclosure, it has a temperature T2, and I have a small gray body inside it, which is T1. Okay, and the surface area of this gray body is AG, and the enclosure has a temperature T2. This enclosure will emit, okay, an intensity equal to sigma T2 with a power 4. Why? Because as we mentioned before, Stephen Poltzmann said that the black body emits a total emissive energy as a function of the temperature and the surface area. But here, if I assume that this enclosure is a black body, so the intensity coming out, or the enclosure intensity or emitting intensity, it will be equal to sigma T square with the power 4. Okay, this intensity will be sent to this black body. What or how much of this power will be absorbed by the black body? So the rate at which this radiation is absorbed by the gray body, not a black body, it's a gray body. So the black body send an intensity to a gray body. The gray body will receive or will absorb a amount of, it will not absorb the whole amount, because there is a certain percentage which is referred by alpha, the absorption or absorptivity of the body, which I showed you in here. Look, if we back to this diagram, you will see here there is absorptivity of the body. So this body will absorb a certain amount of this intensity received, okay, and it will be calculated alpha times Ag, which is the surface area of this gray body, times the intensity which we calculated before. Okay, so the percentage of this intensity absorbed by this gray body, it will be as a function of alpha, which is the absorptive value of this gray body. But the gray body emits radiation at a rate given by epsilon area gray times the intensity of the gray body itself as a function of the temperature. So to make it very simple, if I have a body and this body received some intensity from another body or from an enclosure, this body will absorb an amount of this intensity. Let's say, for example, if I call it I1, so this body will absorb an amount of this intensity which is equal to alpha I1. At the same time, this body emits to the surrounding an emissivity or a power is equal to epsilon G, which is the emissivity of this power, times Ag times sigma T1 with the power 4, because this body over T1, because everybody in this universe and everybody in this life can emit an energy, okay, or emissive power, and this emissive power is a function of its temperature and the emissivity of this body. So this body is receiving some power or some emissive power from another body, which is enclosure in this case, and this body emits to the surrounding and some power which is a function of its own temperature and the emissivity. Okay, so what is the net? What is the net which has been stored inside this power? It will be or what is the net which has been exchanged between the enclosure and this gray body? It will be the difference between the emissive one minus the absorbed one. Okay, clear? So this is the radiation or the net radiation exchange between the black enclosure and the gray body. Okay, in case of real bodies, if I have, for example, here a real body in enclosure of the enclosure is a real body, and this is a gray body, so it will be much more complicated, because there is lots of emissive power from this gray body to the surrounding, and it will be absorbed by the enclosure, and this enclosure will emit another amount of energy to this body, and so on. So to make it simple, when we analyze these equations, or when analyze the radiation heat transfer, we assuming that the enclosure is a black body. So we can use this equation to calculate the net radiation between the enclosure and the gray body. Okay, here there is a small example to explain to you how it works. You are sitting in a room where the room surface has a mean temperature is 18. Your body mean surface temperature is 25. Your surface area is 1.8, treating yourself as a gray body with an emissivity of 0.9. Determine the net rate at which you are losing heat by radiation to your surrounding, as it's very clear here that your temperature is much higher than surrounding temperature, so you will lose some energy or some power by emitting it to the surrounding. So your heat loss rate by radiation, it will be equal to this equation. You can use this equation very clearly, assuming that you are a gray body and you have the emissivity of your body and you have the temperature difference, so you can calculate it very easy. So 66 watts, which is called 66 joule per second, you lose to the surrounding. Okay, if I have two surfaces in real life, not all of the radiance or not all of the radiation beams can be collected or can be received by the another surface. So we assuming something called the view vector. The view vector is the factor which is calculating how much or what is the percentage of the whole beams or whole intensity can be received by another body. So if you want to calculate the heat transfer rate between two bodies and by radiation, you can use this equation. Okay, but remember that you have to calculate this view vector, and the view factor you can calculate it by using this table. There is some equations here, you can use it easily and you can calculate this view factor, or you can use another chart to calculate it. Okay, so this is the real life equations, but during your exams or during your studying, you will assume that the enclosure will be a black body and any body inside it's a gray body. So this is the main equation to calculate it, and this is in addition to the previous law or the previous equation which we have discussed earlier. I hope that this video give you an idea about the radiation heat transfer, and I'm looking forward to hear from you. And if you have any question, please don't hesitate to email me anytime.